So just to remind ourselves here what negative feedback loops are. They're a move in the opposite direction of the change, right? And just to bring back our blood pressure example that we were looking at on Friday, if you had blood pressure fluctuating or deviating from your set point of, say, 120/80, the negative feedback loop would be moving in the opposite direction. So if blood pressure was too high, we'd be moving in the opposite direction to bring it back down, and vice versa. Now, the change or deviation is going to become smaller. We also saw this with our blood pressure example. Again, if blood pressure is really high, whatever that change was, that degree of deviation would eventually become smaller or more diminished as that negative feedback loop closed. And then finally, the reverse change, or the change is what reverses, a negative feedback loop reverses the change from the set point. So it's going to bring us back closer to that set point, whatever it is for that variable. Just to remind ourselves here, this is a continuous process, so you're never in homeostasis in the end. You're always striving to maintain this, this state. Oops, I'm sorry. Technology. Right. Okay, we also got to this example, which I'm going to just go over one more time, just for those who may have missed it. This was an example using body temperature, and our set point for body temperature should be 37 degrees Celsius. And anytime, for any reason, again, usually external circumstances, that set point deviates, or your body temperature deviates from that set point, the body is going to send signals to the integrating centers. Where did we say those usually are? In the brain, right? Usually in the medulla. And that integrating center will take those signals, decipher what needs to be done, and send another output signal to what type of organ or structure? What do we label this as? An effector, right? It's going to send it out to an effector tissue or an effector gland. In this instance, it would be our sweat glands, and that will cause sweating, right? A reverse of this scenario is if we get too cold, if body temperature drops, right? This will incite another mechanism, also through the integrating centers, to help rise the body temperature through shivering, which is usually a spasming of the skeletal muscles that usually generates some heat, okay? And so this is how we had that whole negative feedback mechanism taking place. Again, reminding ourselves here, the change is always in the opposite direction of that initial stimulus, whatever it was, and it's going to be important to bring that back to set point to help close that loop and turn off that initial signal. Now, we talk a lot about negative feedback. Let's mention positive feedback. This is an opposite of what negative feedback is. It's not very common throughout the body. Negative feedback is by far much more common mechanism for homeostasis, but positive feedback is also seen, and we'll talk about some of the examples. Let's talk about what it is first. It's basically an end product that stimulates the process further. So think about something that's being released, either a hormone or a molecule that is going to potentiate this process further. It's not going to stop it the way we saw with negative feedback. So basically the action is amplified by the presence of whatever this end product is. Again, it could be a hormone or another type of molecule. Now, positive feedback contributes to a lot of negative feedback loops, so you hardly see positive feedback existing on its own independently. It's usually incorporated into a negative feedback loop in order to end that potentiation, to end that positive cycle, because we don't typically want that happening indefinitely. All right, let's look at an example here. If you cut yourself and there's an injury to your skin or an underlying blood vessel, there's a process that begins that causes that injured vessel to heal itself. We have clotting factors that are in the blood. They'll make their way to that injury, to that site, and start laying themselves down on top of the injury. And this will continue to happen. So clotting factors will send out more signals that will call more clotting factors, and they'll potentiate that signal until that wound is healed, right? And so when that site is, reapproximated, if it was a cut or something, or healed, that will become what type of feedback? If we finally have that wound being healed, what type of feedback will this turn into? A negative, right? So it's a positive feedback until the wound is healed with those clotting factors, and then it becomes a negative feedback. There are some other examples we'll look at. There's the strength of uterine contractions during childbirth. Those contractions get stronger and stronger until the baby is delivered. That's another way that positive feedbacks can be incorporated into some negative feedback loops. Question?
So positive feedbacks come first, then negative, or is it positive?
So you have positive feedback for the duration that it's required, and then a negative feedback ends that cycle. And so let's look at this example. This has to do with the monthly cycle. So every month, a woman ovulates, one of her ovaries releases an egg, and this feedback cycle is very important in that process. So the pituitary gland is one of our master hormone glands. It's in the brain, the ventral surface of the brain, and it releases one of its hormones called luteinizing hormone, or LH. Now, every month around mid-cycle, the pituitary has to secrete LH hormone, and that LH goes to the ovaries and it's going to potentiate the release of estrogen. So estrogen is now being released from the ovaries. That is going to feed back to the pituitary to increase the LH secretion. And so we have this amplification of the amount of LH and estrogen that's being secreted until we get to a very important event, which is called the LH surge. And don't memorize any of the details here, but just understand the process that's happening here. When we finally have that LH surge, we can shut off this mechanism. And that's where we go from a positive feedback back to a negative feedback. So just to remind ourselves, we hardly ever see positive feedbacks happening independently or on their own, just because we don't ever want this change to be indefinitely potentiated. We always want to end it at some point. Correct. That is a great way of looking at it. So for a small time, the set point here is slightly changed. Okay, we do want to have excess luteinizing hormone. And so the body's going to work to create that environment. It's going to secrete estrogen. Estrogen is going to have a potentiating effect on the pituitary to secrete more LH, and so on and so on. We have that spike in LH. The ovary is going to ovulate, or that egg is going to be released, and we can shut this cycle off. All right? Any questions on this example? Okay, we'll wrap up here by just mentioning two types of regulation that can happen in the body. So there's intrinsic and extrinsic and extrinsic regulation. And we'll see this a lot throughout the course. We'll see it in the cardiovascular system. The heart has very good examples of intrinsic and extrinsic regulation. But basically, intrinsic is where a group of cells or tissue can control itself. And again, the heart is a very good example of this. The heart can control its own rhythm, right? It can determine if the rhythm is too fast or too slow, and to some degree, it can control its own rate and rhythm. Whereas extrinsic regulation is going to be external factors that are controlling the heart. So again, we can see this being controlled through the endocrine system or the nervous system, so through nerves or through hormones, but some factor outside of those cells, something extrinsic, is what is regulating these cells or this tissue. Okay? And the brain is usually the extrinsic factor that is regulating.